Hello and welcome back to CS420, a course on game hacking. If you made it this far, I just want to say good on you for sticking with these videos. Most people quit before this point, and it's a true shame because this is really where it gets interesting. Today we're going to be learning about assembly editing, and this is a fancy way of saying we're going to rewrite a game's code to get it to do what we want it to do. And don't worry if you've never written a line of code in your life, by the end of this video, you will be able to develop your own hacks easily using assembly language. Now, I've mentioned this before, but you can generally break up hacking anything into 3 steps. In this case, we're going to be finding assembly code, changing it, and seeing if it worked. Now, unfortunately, finding assembly code and changing it are 2 very different skills that are both actually kind of hard, right? If you remember memory editing, the steps were memory scanning, memory editing, and then see if it worked. And memory editing is easy, right? You just change the value, right? It's just like a drop down in Cheat Engine. But memory scanning was the hard part. Here, there's a bit of a learning curve to both of them. Finding assembly code actually requires memory scanning, so you have to have that skill. Changing it requires understanding assembly language, and then obviously just observe it. That's not hard. As always, I prefer to teach theory before we get into the skills themselves, so first we're going to learn what assembly code is and how it works, and then we'll dive into how to hack stuff. First, we need to learn a little bit about hardware. Your computer has a CPU. That CPU is responsible for running code. Now, the manufacturer of that CPU decides what code can run on that CPU. This is known as a computer architecture. Desktops, laptops, and modern consoles fall under the x86, x64 architecture, and that's the variant of assembly language that we're going to be focusing on. Now, smartphones and handhelds tend to use ARM assembly. And ARM is a cleaner, simpler, modern assembly language. And because of that, it's more power efficient. The battery life on these devices is really good because the CPU is simple. Interestingly enough, Mac just announced a new M1 laptop that uses an ARM processor. And because of it, it blows other laptops out of the water when it comes to the battery life. And unfortunately, it can't run, if you have a game on your old laptop and you want to run it on your new M1 Mac, it's not going to work unless you emulate it, right? Same way you play GameCube games in your computer, right? Now you need an emulator to run your old Mac games on an M1 laptop. The last major architecture is PowerPC assembly, and some older consoles use it, and you probably will never see it unless you get deep into hacking these consoles. Now, obviously, since the vast majority of you are going to be hacking on a desktop or laptop, I'm going to be focusing on x86, x64 assembly, but everything that I teach you here will apply to these other ones. We've touched on this before, but now it's time to revisit this diagram. Allocated objects like these green and purple areas are just data. We know that. And as I hinted at before, when you zoom into an exe or DLL, there's static data, but there's also static code. The way it works is that exes and DLLs are broken up into sections. Here we have data, and here we have code. And we've learned a great deal about data already. Zeros and ones grouped by 8s. These groupings are known as a byte. Multiple bytes can be paired together and interpreted in different ways to give us booleans, integers, strings, and so on. So now it's time for us to learn about code. Just like with data, we know that it must be zeros and ones, but that's not a very useful mental model, so we need to learn more about the structure that makes up code. So if this is our game's code, as always, group it into bytes. Now we can group those bytes into assembly language instructions. And don't worry about understanding this stuff yet, it'll all make sense eventually. The only thing you need to know is that bytes can be grouped into instructions. The first 6 bytes make up this move instruction. The next byte makes up a no-op instruction, which stands for no operation, which we will learn about very soon. The next 4 bytes are a subtract instruction, and so on. One thing to note is that when people say the phrase machine language or machine code, they're talking about the raw bytes, right? This FF, E8, 7B. We call that machine language. But once we group them into an instruction, that's when we call it assembly language. We can take the same information and stack it vertically instead of horizontally, so we have the bytes on the left and the corresponding assembly language on the right. And this is how most of our hacking tools will display assembly language. Let me jump into a quick demo in Squally where I demonstrate the relationship between machine code and assembly language. Here we're jumping into an example where the enemy is firing a fireball at me. And you can go in and you can view the assembly code of this fireball. right? So this is the original code that sets the speed of the fireball, and you can see the corresponding machine code on the side. So this is the assembly language, and this is the machine code. And if you change the assembly, the machine code will change as well, obviously, right? If I start typing stuff here, push EAX, there's an extra byte at the end here. And if I delete it, that 50 is gone. Now what's neat about Squally is then I can go in and start editing some of this assembly language to reflect the fireball back at the attacker here. And what's neat is if you go into Cheat Engine, you can actually see that the changes took place in memory, right? This is the code that I just injected into the game. So basically, I'm taking the tools that Cheat Engine provides and just putting them in the game, so you don't even need Cheat Engine. And that way, when you do move to Cheat Engine and you start writing assembly code in there, you've already seen it before in this game. You can actually get a lot done with assembly language. This is the original Roller Coaster Tycoon game, and it was written entirely in assembly language. Now, this is really rare. Programming in assembly language is tedious, and it's easy for programmers to make mistakes. To solve this problem, we invented languages like C and C++. One line of C++ turns into many lines of assembly, making it easier for the programmer to organize their code and understand what's happening. Turning C++ code into assembly is known as compiling. So let's learn how the compiler works. Most games are written in C++. The game developer can then compile that C++ into machine language, and as a hacker, this is unreadable to us, right? We can't read zeros and ones, so we disassemble that machine language into assembly language. We can then edit this assembly language to reprogram a game to get it to do what we want it to do. Now, theoretically, it's possible to decompile assembly language back into C++, but this doesn't really work. To give an analogy, compiling is kind of like cooking a meal, and that means decompiling would be like uncooking a meal, right? It doesn't really work. Information has been lost in this case. And let me hop into an example to show why going back to C++ isn't very useful. Okay, so here I've hopped into a website called godbolt.org, and it basically just shows you the relationship between C++ and assembly. So I've written some very basic C++ code here, right? I initialize 500 health. I create random damage between 0 and 50, and then I update health to be, whatever 500 minus the random damage is, and then I print that out. Now, if you mouse over code over on the left, it'll show you the corresponding assembly on the right. And I have this int health equals 500. Now, if we look at the corresponding assembly language, this is it. This one line here sets up health. Now, interestingly enough, you do not see the word health, right? That gets lost during compiling. And so if we try to decompile this assembly back into C++, we will lose this variable name. So that's why it's kind of a one-way process, right? Information gets lost during compiling. So coming back to this diagram, we know that we'll be editing the assembly code of a game. Or more accurately, right, I always like to show the virtual memory. We are going to be hacking the code section of the exe, or perhaps a DLL, after they're loaded into memory. Now, unfortunately, there are some scenarios when this type of hack does not work, and we need to be very aware of these scenarios. To understand this, we need to learn about games that are made in technologies other than C++. Now, I'm going to gloss over these technologies significantly. There's no point for me to go into details now because most of these topics will be their own video later. So don't worry about memorizing anything on these slides. Just try and grasp them maybe at a high level what's going on. The second most common technology you will encounter is C#. Many indie games today are developed using Unity Engine, and Unity Engine uses the programming language C#. Now, C# compiles in a special way known as just-in-time or JIT compilation. And we're not going to get into the mechanics of that yet. Just understand that all it means is that code is actually created while the program is running and therefore is not static. Games made in Java work exactly the same way, although there aren't very many of these. I think RuneScape and the original Java version of Minecraft are the only two big ones. Console games running on an emulator are also just-in-time compiled, right? You boot up your GameCube or Wii ISO file, feed that into your emulator, usually Dolphin, and it translates this PowerPC assembly language into x86 assembly language. As a result, the generated assembly language is not static. There's also this engine called GameMaker targeted at newbie developers, and a few semi-popular games have been made using this engine, most notably Undertale. And what's special about GameMaker is that there is no generated assembly code. All GameMaker scripts rely on existing assembly code in the GameMaker engine. Web browser games work very similarly. No assembly code is generated. JavaScript, Flash, HTML5 all goes through browser code or plugin code, as do Python games. However, there are no popular games written in Python, so you're very unlikely to encounter this one. Putting this all together, there are three categories. The first category would be games written in C++, which store static code in EXEs or DLLs. Next are just-in-time compiled languages, like C#, Java, and console emulators, which store code in the heap. And I don't think I mentioned this, but the heap is any of these allocated non-static objects. And the last category are scripting languages like Python, GameMaker, and web browser languages, which do not generate assembly language at all. So what does this mean for us as hackers? Assembly editing works really well on C and C++ games because the code is static. If you write a hack where you change the assembly language and you reboot the game, that hack will still work the next time you try it. Unfortunately, if you try this on JIT languages, right, games written in C#, Java, or emulators, that code is not static, therefore it's harder to reapply your hack when you restart the game, which is why I generally don't recommend it. And when it comes to scripting languages, assembly editing almost never works. For example, if you tried to edit the assembly code of a browser game, you would actually be editing browser code, not game code. Sometimes this works, but usually it doesn't, and you'll just crash your browser. So now that we know when to use assembly language, let me teach you how to figure out what technology a game uses. To figure out if a game is written in C# or C++, simply find it. So I'm going to be looking at Ori and the Blind Forest, right? I can go into Properties, Local Files. So I'm just finding where it is on disk, browse local files, right? So what we're going to be doing is looking at what DLLs the game uses, because that's a dead giveaway. There are a few dead giveaways, right? If you see the words mono, that usually means C#. But if you dig around and look at the DLLs the game loads, right? So here I see assembly C#.dll and mono security, right? Those are Unity engine.dll. Those are dead giveaways that this game is definitely written in C#. And so assembly editing is pretty dicey, right? Probably shouldn't be using it, but you can if you really want to, right? But not ideal. So now let's look at another example. We're going to be looking at Batman Arkham Asylum, this Game of the Year edition. So same thing, browse local files. Binaries is a good place to start. And all we have to do is kind of thumb through and see if we see anything that would give away what technology this uses. And there's nothing in here except I see this UE3 shader compile worker. So if you see something like UE3, UE4, UE5, it probably means Unreal Engine, which is C++. So that's a dead giveaway that this is C++. If you have written a game in Unreal Engine before, another giveaway is like these config files. So that's another case where you can kind of just look through the files to get an idea for what technology the game uses. Okay, last but not least, let's look at Squally, right? Browse local files and see what language this is written in. I mean, the answer is obviously C++, but let's take a look anyways. We notice that there is this empty private folder, this resources folder, which is just images and stuff. So the only things in here, there's one DLL and 2 EXEs, right? That's not a lot of information, but actually sometimes a lack of information is all the information you need. Because there's only an EXE and one DLL, it's C++, right? If you can't figure out if it's C#, it's C++. I said earlier that there were two big steps in hacking assembly language, finding it and changing it. So let's learn how to find assembly code that we want to change. In a large game, there could be millions and millions of lines of assembly instructions. And as a hacker, our goal is just to find a few of them. For example, we want to find the code that hurts a player or the code that takes away our gold when we buy items. Let's say our player's health is stored here in the player object. Now in a C++ game, all the code is stored in the exe, so we know that code somewhere up here is responsible for updating the player's health down here. Our goal is to find that code. There are a couple ways to do it, but I'll focus on the most common way that game hacking tools do this. All CPUs have debugging features that are supposed to make it easier for developers to find bugs in their code and fix them. However, we can use those features to help us cheat. We can put something called a data breakpoint on the player's health, and it'll tell us exactly what line of code in the exe tried to access or update the player's health. As always, this happens in virtual memory, and so here's that same image flattened out to give you a better perspective here. Let's hop into a real example now. So I've already booted up Squally. I scanned for health and I found it, right? This number is Squally's health. He has 24 right now. If I change this to 32, health goes up. I can change it back. And we want to find the code that edits this health. So what I can do is right-click, find out what writes to this address. This will find out what actually updates health. If I wanted to figure out what code was reading health, right? If it was like a comparison to check for death, it might be doing a read, but I'm curious to see what's actually updating health, right? Taking damage. So I'm going to find out what writes to this address, and I'm going to go ahead and take some damage. Okay, I took 5 damage, and we see one instruction comes into this list here. So what we want to do is add this to our code list, and I'm going to give it a name like update health. And now it's in our code list, so we can stop and close this out. And what's cool is we can actually just right-click on this and replace it with code that does nothing, right? And you can restore it back to the original if we want. But what this does is if we look over here, the original code is move, ESI, EAX. We'll learn about that stuff later. What we could do is right-click, replace with code that does nothing, and it fills in these no-op instructions. This is code that does nothing, no operation, right? So it replaced our update health code with nothing. So now if we go ahead and take some damage in the game, we'll see that nothing happens. Cool. Now, unfortunately, that same code actually applies to enemies too. So if I go ahead and hit this enemy, you'll find that the enemy still has full health, right? So there's sometimes things you have to look out for. Depending on how the game was programmed, this may be God mode for just the player, or it may be God mode for everybody. There are just some pitfalls. Okay, so I've gone ahead and rebooted Squally to show something really important. I reattached Cheat Engine to the new version of Squally, and we see that the health is no longer valid, right? Because this was a dynamic address, right? It was not in static memory. So it now just points to some garbage. This is no longer useful. However, if I go in and look at this code, that's still valid, right? Because code is static, the address never changes. So anything in our code list will still work as long as the game is C++. Remember, in emulated games or C# or Java, that'll not be true, but in C++, any code you find is going to work forever. So I can replace it with code that does nothing, right? And then this strange God mode for everybody hack will still work, right? They just took no damage. So we learned how to find code that we're interested in and maybe fill it with some no-ops, and that's good enough for 90% of the cases, right? Usually as a hacker, we're just disabling things. We find code that hurts the player, fill it with no-ops. We find code that takes away the player's gold, fill it with no-ops. But there are some cases where it becomes very valuable to write custom assembly code, and in order to do that, we need to understand assembly language. The first topic we need to cover in assembly language is the idea of a register. Registers are temporary storage in the CPU that is used by assembly language. Before we get deep into registers, we need to understand how code actually runs on your hardware. We learned that when a user double-clicks an exe, it's copied from your hard drive into RAM. However, we need that code to run on the CPU, and the CPU has incredibly small storage, so we can't just copy all the game's code over. Instead, code is streamed into the CPU line by line. It's exactly like streaming a video through Twitch, right? On Twitch, assuming your internet connection's good, more video just keeps coming in and you will never experience interruptions. The CPU works similarly, and more code keeps streaming in line by line. However, there's a slight problem. Sometimes code needs to access data. The CPU might run some code to read the player's health, update it, apply some damage, and then write it back to RAM. Unfortunately, constantly accessing RAM from the CPU is actually quite expensive, and to solve this, they put a very small amount of storage on the CPU called registers. The further away the hardware is from the CPU, the slower it is to access, right? Hard drives store a lot of data, but their access is fairly slow. RAM stores a moderate amount of data, and it's pretty fast, but the access is not nearly as fast as the data on the CPU. But CPU storage is so small that we need to zoom in. Okay, so here's RAM and CPU, and I got rid of hard drive memory, and it's still nothing compared to RAM, right? We need to zoom in again. Okay, so RAM was shrunk down to fit on the screen, so it's no longer to scale, and the CPU memory is now visible on the right-hand side. And to get data and code into the CPU, it passes through a series of hardware caches. For example, code ends up in this L1 code cache, and data streams through to the L1 data cache, and some of that ends up in registers. Now, fortunately, hardware engineers are super smart, and they hide all of these caches from us. So as far as a game hacker is concerned, there is only RAM and registers. If we want to change something, usually we need to load it into a register first. So we might load the player's health into a register. Then we might load some damage we want that player to take into a register. Then we subtract the two with code, and then we write it back into RAM. Here is an example of registers in a 32-bit game. On the left-hand side, we have the name of the register, and then we have a 32-bit value stored in that register, right? 32 bits is 4 bytes of information. Now, while a program is running, these registers are constantly updating. If we were to freeze that program for a second and take a look inside the registers when the player is about to take some damage, we might see something like this. The register EAX contains the value 64, which is 100 in decimal, right? That might be the player's health. And the register EBX contains the value 5, which might be the damage. We would then have some code that runs that subtracts 5 from the player's health before writing it back into RAM. In a 64-bit game, the registers take on a different name and can store more information. Now they can store 64 bits of information, or 8 bytes. And there are actually some bonus registers available for 64-bit games. And the chart was rotated to fit on the screen. So in a 32-bit game, we have the ones we saw earlier, EAX, EBX, all the way to EIP. And on a 64-bit game, we have those as well, with an R instead of an E. But we also have these new registers available to us, R8 through R15. And even though they're named differently than the other ones, they work exactly the same. So x64 assembly is used for 64-bit games, and x86 assembly is used for 32-bit games. And I know what you're thinking, why isn't it called x32 assembly? Well, x86 is actually named after some early CPUs invented by Intel, and when 64-bit computers came out, they had to think of a new name, and they went with x64. And it's really dumb, but that's just the way it is. Figuring out if a game is 64-bit or 32-bit is really easy, right? When you open up your hacking tools and look at the code, if you see R's, it's a 64-bit game. If you see a bunch of registers that start with E, it's 32-bit. Otherwise, hacking them is almost exactly the same, and usually the only difference is what register you type in, and it's just a difference of that R versus E. It's generally very simple. Different registers are used for different things, and a good rule of thumb when you're starting out is never mess with a register that ends with P. For example, the RIP and EIP registers contain a pointer to the next instruction that will run on your CPU. So if you change the value in these registers, you disrupt the flow of that program, and it most likely will crash, again, unless you know what you're doing. For game hackers, everything else is fair game, right? These first 6 and then all of the bonus R registers are fair game for editing and using for our hacks. Now let me show you a few examples. First, I'm going to show you a few examples from Squally to teach you some basic instructions. Then I'll show you how to write a hack from scratch using Cheat Engine. In Squally, I put an in-game manual for the most common assembly instructions. So right now we're going to focus on the stuff on this left-hand side and these, and we'll put off push and pop for now. We'll learn about those later. So let's take a look at increment. The most basic form of increment takes the form inc and then a register. So this one will increment whatever value is in register ECX. So every time I click this, the value goes up by 1. And you've seen this before, but these brackets indicate that there's a pointer that needs to be followed. So instead of incrementing EAX itself, EAX is a pointer, and it follows that pointer into memory, and it increments the value that it points to. So here, increment the value at EAX increments the value in RAM, in memory. And there's this other form too, where we follow the pointer and go down 8 bytes, which is 2 integers worth of data. So if I do this, I go follow this pointer at EDI, go down 2, and that's the value that's getting incremented. Decrement works exactly the same, except it decreases by 1 instead. Add is different because there are 2 operands, right? We have the register and how much to add to it. So we have add EAX 2, and if we execute this, EAX increases by 2 every time. Now what's special about these instructions that have 2 operands is you can use 2 registers, right? You can add ECX and EDX together, and the result will be stored in the first operand. So ECX, you add EDX to it, and what do you think will happen here? ECX is 12, EDX is 3, and it just keeps increasing by 3, right? So this first time it becomes 15, because 12 plus 3 is 15. And as before, there are the pointer versions of these operations. So here we have the value that EBX points to. We're adding 10 to it. So this increases by 10 every time. And I'm not going to walk through all of these, but if you want to slow this down and take a look at what's happening, by all means. Subtract obviously works exactly the same, but it's subtraction instead of addition. And another important one that you need to know is the move instruction. How move works is that it just copies a value into that register. So we have move EBX 200. The value is 2048, and it gets overwritten with 200. We have move ECX EDX, and that will overwrite whatever's in ECX with EDX. Same here, move EAX 10. It'll just put 10 in that register. And an important thing to note is that you can never have 2 things with brackets in one instruction, right? You can't move the EAX in brackets, EBX in brackets, because that goes into RAM twice and it's too slow. Like I said, accessing RAM from the CPU is expensive, so you're only allowed to do it once per instruction. Neg is a very easy instruction. It simply negates the number. And mul is a very simple instruction too. I'm not going to get into it either. It's just, it works like add and subtract, except now it's multiplying instead. Now div is the most infuriating instruction of them all. The way it works is not like multiply. You only have one register that you pass to divide. And you might be thinking, well then how does it know what to divide by? Well, actually what you're passing is what you want to divide by. EAX and EDX are automatically included in the calculation. So for example, EAX has a value 120, ECX has a value 12, and when you click this, EAX gets divided by whatever you passed, so ECX in this case. So 120 divided by 12, you get 10. And if you click it again, 10 divided by 12 in integers is just 0, but the remainder gets stored in EDX. So it's super weird. EAX is what gets divided, and the remainder gets thrown in EDX. Honestly, if you can avoid using the div instruction, I would, because it's very frustrating to use. But the only thing you need to know is that it works differently than everything else. Now I want to demonstrate writing custom assembly code. And I'm going to be doing it on a very simple game, Minesweeper for Windows XP. And the reason for that is this is a fairly advanced topic, and I do not want to get into a complex game to show this, right? Writing assembly code is a skill that takes hours and hours and hours to build. And that's the entire reason I developed Squally, right? Is that you really need to put in the time to get good at it. And me in a small lecture video, I'm not going to be able to get the point across very well. So the best I could do is show the most simple example I can think of, but I really highly recommend, just developing your own hacks after this and use this as a jumping point into your own stuff. So I've gone ahead and found time, which is a 4-byte integer. And if I start the game, this time increases as the timer in the game increases. And our goal is going to be something simple. Instead of increasing by 1 every tick, we want to increase it by 2. So what I can do is right-click on this, find out what writes to this, and we instantly find this increment instruction. So add it to our code list, increment time. Okay. open it in the disassembler, and we see this increment instruction that takes up 6 bytes of memory. And our goal is to actually just change this from increment to add address 2. So add 2 to that address instead of 1. Now the problem is that if I hit OK here, it's going to warn me that the new code I put in is 7 bytes and the old code was 6 bytes. And I'm going to hit cancel here. The problem with that is that it would start bleeding into these next instructions and corrupt them, and it would cause the program to crash. So the issue, to put it more succinctly, is that I am trying to write code that does not fit here. And to solve this, Cheat Engine gave us some very useful tools. I'm actually going to show it in diagram form first. So we have our code here somewhere in this exe. In Cheat Engine, what it can do is it can allocate a new object for us where we can write more code, and we can jump to that, start running the code here, and then jump back, allowing us to write more code than we could fit in the exe itself, right? Because the exe is a fixed size, and we want to be able to write new code. So generating a new block, allocating new memory, and writing code here, and then running that is the correct solution. So we're going to go into Tools. We're going to highlight the instruction first, right? This increment instruction, Tools, Auto Assemble. And when we need to write an enable and disable section. And Cheat Engine gives us a tool to kind of fill some of this out for us. So after we write enable and disable, we go into code injection, hit OK. Again, we need to have our increment instruction highlighted here, otherwise it won't fill in properly. And I usually delete some of this auto-generated stuff. I delete original code and this comment, and I delete original code up here. So this enable tells us what happens when we enable the cheat, and this disable says what happens when we disable. So the first thing you notice is that it allocates that memory like I was talking about, and when you disable, it deallocates that memory. And where the instruction used to be, it is now jumping to that allocated region here where we can start writing our code. So that's what this jump instruction does. It says, okay, jump to that new allocated piece of memory. So here we have inc and then the original address. So now we can write add 2. And we'll go ahead and save that or assign it to the cheat table, and we can exit it out, and then we can call this script increment by 2. And now when we enable this, we'll notice that time goes up by 2 every tick instead of 1. And look at the difference in memory on the left-hand side here. See, we have this jump and a no-op, and that's where the increment used to be. So you can kind of see the difference here. So jump takes 5 bytes, and the old instruction was 6, so it's jump and a no-op because we need to fill up 6 bytes, and a jump is 5, right? And this original code was 6. And if we hit space, it'll follow this jump, and we can see this is like the new block of allocated memory. There's question marks before it because nothing's allocated there. And we have all this space to write our code. But we're just using a little bit. See, we have our add instruction, and then we jump back. That's where we return right afterwards. So very straightforward, a very simple hack. But this is really the building block for writing more fancy assembly later. So next video, we will finish off assembly language, and assembly editing is the hardest skill you will learn. So if you can learn this, everything else we cover will feel like child's play. And once we're done with assembly, we can get on to exciting topics like hacking online games, C# games, browser games, developing bots. And as always, if you have any questions, feel free to reach out. Thanks for watching. Bye.